Interference in thin film due to reflected light. Before I start this, let us find out how we get the two coherent sources. How to obtain two coherent sources. These coherent sources are obtained by, there are two methods. The first method is by division of wavefront. Division of wavefront. As you know that two independent sources cannot be coherent. So the coherent sources should be derived from the single source, and that can be done by dividing the wavefront. And this method is used in Young's double slit experiment. It is also used in Fresnel biprism and Lloyd's mirror. In this experiment, we get the two coherent sources by dividing the wavefront. Suppose wavefront is traveling in this direction, then it is allowed to pass through two pinholes. So this wavefront then divide into two wavefronts and we get the two coherent sources. Second method is division of amplitude. And in this method, what is happened is the beam is optically divided by partial reflection and refraction. So in the transmitted light by partial refractions, we get the, instead of one beam, we get the two beams, or we get a multiple beams, which are derived from the single beam. And so that is the second method. Now in this method, we are going to study interference in the thin film due to reflected light. In this case, we get two coherent sources by dividing the amplitude. And in this case, the example is soap bubble. We see the beautiful colors in the soap bubble in reflected light as well as in transmitted light. Here I'm going to explain you the interference in such a thin films due to reflected light. So let us first draw the diagram of the thin film. Let's say that the thin film is enclosed between these two horizontal lines, and thickness of that film is T. What we have here, I have shown, is parallel thin film of thickness T and refractive index mu. Refractive index of this film is mu. Then let's say AB is the incident ray. This is AB and this is the incident ray. AB is incident ray. Let me show you the normal at point B. I am going to draw normal at point B to the film. So this is normal to the film at point B. Then what happens at point B? AB is the incident ray. Then that ray is partially reflected and partially transmitted. Let me show the ray properly. This is ray AB. A and B is the incident ray. Then at point B, it is partially reflected. Let's say it is partially reflected along the direction BR and partially transmitted it is partially transmitted along the BC. Let's say this point is C. So it is at point B, the ray is partially reflected along BR and partially transmitted along BC. This is point C over here. So this point here is C. Then at point C again, the ray BC is partially reflected and partially transmitted. However, we are studying in this case interference in thin film due to reflected light. So at point C, I am not going to show transmitted ray or a refracted ray. I am showing only reflected ray from point C. So it is reflected, let's say, along CD. Then again at point D, this is point D over here, at point D, it is partially transmitted and partially reflected. And I am showing only partially transmitted ray. So it is, let's say, partially transmitted along the direction DR1. Now you can see here, AB is the single incident ray, and from that ray, due to reflection from the thin film, I got two reflected ray BR and DR1. So here, two reflected ray BR and DR1 obtained from single ray AB. So you can say that this BR and DR1, two rays, which two reflected rays which are derived from the single ray AB, and so they are coherent. How we got these two rays BR and DR1? By partial reflection and refraction. And since we got it by partial reflection and refraction, there we are dividing the amplitude and we got the two rays. So BR and DR1 are coherent rays. What we have to find is, in this case, the path difference. What to find? We have to find path difference between rays BR and DR1. So we have to find path difference between BR and DR1. As this BR and DR1 both are parallel rays, and these parallel rays interfere and produce the interference pattern. Now, what kind of interference pattern they will produce, that depends on the path difference, and so we have to find the path difference. In order to find this path difference, what I am going to do is I am going to extend this CD in the backward direction so that it will meet this normal. So from point C, what I have done is I have extended this in the backward direction. So this is my point, let's say P. So I have extended this CD in the backward direction so that that line intersects at point P to the normal. Then let's write, and one more thing I am going to do is I am going to draw normal from point D on ray BR. So this is the normal. Let's say this point is E. So DE is the normal on BR. And one more normal I'm going to draw. I'm going to draw normal from point B on CD. And that point is, say, F. So in this case, what we have got? We have got two normals, this DE and BF are normals on rays BR and CD respectively. Then let's find what would be angles, the different angles. Here this is incidence angle, this is also I, this one is 90 over here, this is 90, and so this one is 90 minus I, and hence this angle is equals to I. And if I draw, one normal over here at point C, then this angle is also R and this angle is also R. If I draw one more normal at point D, then this angle is also equals to R. Now this angle over here, since BF is the normal, so this angle is 90 degree. And so this one is 90 minus R, and therefore this angle is R, angle of refraction. This is angle of refraction R. Now in this case, this BQ equals to T, the thickness of the film. BQ equals to T, and that is equals to QP. In this diagram, BQ is equals to T and that is equals to QP. So BP is equals to twice the thickness of the film. Now here in this case, this BC is equals to PC. What we get here as per the geometry, BC is equals to PC, and therefore angle P is equals to R. So this angle is R over here. Let's see the diagram now carefully. What we are going to find is path difference between BR and DR1. For that we have done such a extra geometry. So path difference, first let's find first geometrical path difference. It all starts at point B. At point B, ray is partially reflected along BR, partially reflected along BC and then CD. So by the time this refracted, or you can say transmitted ray travel a distance BC plus CD, the reflected ray BR travel a distance BE as per the geometry. So we can write here geometrical path difference between rays BR and DR1. This is the two reflected rays. And geometrical path difference between them, let us say GPD, geometrical path difference, is equals to BC plus CD minus BE. Let's see the diagram. So here in this diagram, BC plus CD minus BE is the geometrical path difference between the rays BR and DR1. It is because by the time this transmitted ray travel a distance BC plus CD, the reflected ray BR travel up to point E. And so its a geometrical path difference between them is BC plus CD minus BE. Then what would be the optical path difference? Now this BC plus CD, this is the path travel in the film whose refractive index is mu. See this BC and CD, this BC and CD is the path traveled by the ray in the film whose thickness is T and whose refractive index is mu. Therefore, optical path difference delta is equals to mu times BC plus CD minus this BE is the path traveled by the reflected ray BR in the air. This is in the air. Refractive index of air is 1. So this term is at it is BC plus CD minus BE. And this is our equation 1. Then according to Snell's law, the mu is equals to sin I upon sin R. Now let's see how much is the sin I here. See, this is the angle I over here. And sin I is equals to BE upon BD. Sin I is equals to BE upon BD. And sin R, this is the R. Sin R is equals to FD upon BD. So let us write that sin I is equals to BE upon BD, and sin R is equals to FD upon BD. In this diagram, this BD will cancel with this BD, and what we get is mu is equals to BE upon FD, or BE is equals to mu times FD. What we have done here is we have calculated this distance BE in terms of optical path difference. Then let us substitute equation 2 in equation 1. Substitute equation 2 in equation 1. Then you get optical path difference delta is equals to mu times BC plus CD plus CD. But CD I will replace. Let's see what is the CD. This is point C and this is point D over here. So instead of writing CD, what I will write is CF plus FD. Okay, here I will write CF plus FD instead of writing CD. So here BC plus CD, this CD. Instead of this CD, I will write CF plus FD minus BE. But this minus BE is equals to mu times FD. I will take this FD inside the bracket, and common is a refractive index. So in this case, this FD cancels with this FD, and what we get is optical path difference delta is equals to BC plus CF. That I will write as mu times PC plus CF. Why I wrote that? Because BC is equals to PC. Okay, this BC is equals to PC. Let's see the diagram. This is PC and that is equals to PC. Here also I wrote BC is equals to PC. And so PC plus CF. And that I will rewrite as PF. Instead of writing PC plus CF, I am writing PF. And this is equation 3. Why I wrote PF? PC plus CF. Let's see in the diagram. This is point P, this is point C here, and this is point F. So PC plus CF is equals to PF. And that is my equation 3. Now here, let us consider triangle B, P and F. In this triangle, angle P is equals to R. Let's see the diagram. What I am considering? I am considering here the triangle, this BPF. This triangle I am considering, and this angle is I over here. So if this is R, what would be cos R? Cos R is PF upon PB. So let us write that. In the triangle BPF, angle P is R, and therefore this cos R is equals to PF upon PB. But this PB is 2t, and therefore PF is equals to 2t cos R. This is equation 4. And we wrote that since this PB is equals to twice the thickness of the film in the diagram. See, from here to here, the thickness is twice T, because here B cube equals to QP. So PB is equals to twice T. So this is what I got. Now I will substitute this in the equation 3. Substitute, substitute in equation 4 in equation 3, and I get optical path difference delta is equals to mu times 2t cos r. So I will write 2 mu t cos r is the optical path difference. But here we must note that when light is reflected from the denser medium, what happens? When light ray is reflected from denser medium, its phase changes by pi, or path changes by lambda by 2. So this concept, we have to check that when light is reflected from denser medium, its phase changes by pi, or its path changes by lambda by 2. We are talking here in terms of path difference. So we have to find out if there is any reflection from denser medium. Let's see the diagram. Now we have two rays, this BR and DR1, these two rays. We have to find, is there any ray reflected from the denser medium? See at point B, the BR is a reflected ray from the film. Film is the denser medium. So BR, our ray BR, is reflected from the denser medium. So there would be path change of lambda by 2. Let's see what happens to the ray dr. To get the ray dr, first we have refraction or transmission at point B. So when there is a transmission, no change in the phase or path. It is transmitted along BC. At point C, it is reflected, but it is reflected from rarer medium. This is the air. Air is the rarer medium. This is the film over here. Film is the denser medium. So at point C, there is a reflection, but that reflection is from rarer medium. So no change in the path or the phase. Then it travels along the direction dr, and then it is transmitted along the direction dr1. So there is only one reflection for the ray dr1, but that reflection is from the rarer medium. But for the ray BR, there is a reflection from the denser medium. So our path difference is what? BC plus CD minus BE. So instead of taking just minus BE, we have to subtract the path of lambda by 2. So in this equation, we got this delta is equals to twice mu t cos r minus lambda by 2. Okay, this is due to reflection of the first ray BR from the denser medium, and that's why we have added that, subtracted that lambda by 2 over there. So this is the path, resultant path difference between the rays BR and DR1. Now when this part difference 2 mu t cos r minus lambda by 2 is equals to n lambda, you get constructive interference. But this side also there is a lambda, this side is also lambda, so let us simplify it. Then we get 2 mu t cos r is equals to n lambda plus lambda by 2, and that is equals to 2n plus 1 lambda upon 2. That is when this 2 mu t cos r is equals to odd multiple of lambda by 2, where n starts with 0, 1, etc. So when 2 mu t cos r is equals to odd multiple of lambda by 2, we get constructive interference in the reflected light from the thin film. Then when this 2 mu t cos r minus lambda by 2 is the path difference. When this path difference is equals to 2n plus 1 lambda by 2, we get destructive interference. So let us simplify this. Transfer this lambda by 2 to that side. Then we get this 2 mu t cos r is equals to 2n plus 1 lambda by 2 plus lambda by 2. So after simplification, what we get is n plus 1 lambda by 2. Sorry, n plus 1 lambda. What we get is n plus 1 lambda, that is 2 mu t cos r. But in this case, see, if n is integer, then n plus 1 is also integer. So instead of writing n plus 1 lambda, I will simply write n lambda. So when this 2 mu t cos r is equals to n lambda, what we get is destructive interference. So you should note the conditions. 2 mu t cos r is equals to n lambda, destructive interference in reflected light from thin film. And when this 2 mu t cos r equals to odd multiple of lambda by 2, we get constructive interference in thin films due to reflected light. Thank you.